back and let's go ahead and get to problem 2. I'm just going to go ahead and delete a lot of this notebook that I've been playing around with, working with. Actually, let's go ahead and we're going to let's get our notebook a little bit set up for some of these mechanics problems. Now that we went through problem 1, let's quit our notebook and let's get going to see what this problem has to offer us. So let's go ahead and let's take a peek. So I'm making a new start company, creating an automatic saran wrap mapping machine that will automatically wrap, saran wrap polymer over my Tupperware. You can see a schematic of what the machine will do below. So I apply the loading state, depicted above. The Tupperware lid is lubricated. Now this robot was designed by a student who didn't take Engine 45. I heavily thought Hooke's law was the key equation when dealing with mechanics. So they designed the robot to make sure that epsilon 3.3 did not exceed the yield strength of the black curve above. So, or actually below. So let's go ahead and let's look at what is that yield strength. So we need to make sure that we do not exceed essentially our epsilon 3.3. Let's just say this is our yield strength here. So our yield strain here. So sorry, it's a black curve. So let's just say approximately this is our yield strain. So we need to make sure that epsilon 3.3 is going to be equal to at maximum this kind of 0.01. So that's going to be kind of our value that we need to hit. So that was kind of, again, that we were designed. So epsilon 3.3 is equal to 0.01. So this is kind of the state, 10 megapascals. We're kind of stretching it in both directions here. So with this in mind, again, we're lubricated essentially. So, this is our Tupperware lid, or this is kind of our, Tupperware. We're going to wrap this over our Tupperware lid. So there's no friction, essentially. We're well lubricated. So let's look at our stress state. So first off, saran wrap, polymer. So we know what? Young's modulus, 1 times 10 to the 9 pascals. Nu is equal to 0.4. Let's go ahead and put that already into our notebook. So my y is equal to 1 times 10 to the 9. My nu is equal to 0.4. And we're good to go there. So, got that. What about my stress tensor? Well, I know that there's a stress in the 1,1 direction here. So I've got a stress in the 1,1. That's going to be 10 megapascals. So this is all going to be MPa. So I also have a stress in the 2,2 direction as well. Actually, we're not, I don't know if we're quite sure, but we could kind of assume that that's going to be the same value as well. Actually, we can't really assume that. We know that there's some stress there. So actually, we don't know. We know that in the 2,2, actually, let me erase this. We know this stress here. So this is going to be 10 MPa. But we don't know the stress in the 1,1 direction necessarily. And then, is there going to be any stress in the 3,3? No. I mean, there's nothing, again, that material is going to change, but there's no, it's free to expand or contract. Whatever is going to happen, it's going to contract here. And the rest, well lubricated, so we're 0, 0, 0, 0. So we don't know what that is. What about our strain tensor? So I know that there's going to be a strain in the 3,3 because we said that strain 3,3, we're kind of optimizing it to be like this. There's also going to be a strain in the 1,1, and there should be also a strain in the 2,2 direction as well. And we should know that strain in the 1,1 should most likely be positive, strain in the 2,2 as well, but again, we'll get to that in just a second. So we also know that the strain 3,3 is probably most likely going to be essentially this negative value here. So it is going to be negative strain here. And then here, 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 everything else is going to be 0. Sorry, there, it's going to be 0. So we know this, so tick. We don't know this, we don't know this, and we don't know this. So let's write a series of equations to kind of solve for this. So I know that my strain in the 3,3, I know it's going to be negative. So let's go ahead, because again, we're pulling, so it will shrink. So E33 is equal to minus 0.01. I also know that my sig 2,2 is equal to 10 times 10 to the 6. Sig 1 I don't know. My sig 3,3 I do know it's 0. I know that and I don't know the rest of these values. So let's go ahead and solve. So I need to solve a series of equations. So I know that E11 is equal to 1 over y sig 11 minus nu times sig 2,2 plus sig 3,3. So do that. Here we go. Sorry. Here. And so I'm going to copy this. So this set it double equal. So I'm going to copy this. I'm just going to change 1, 2. And I want to solve for, I don't know sigma 1, I don't know E11, and I don't know E22. So this is going to be E22. It's going to be E33. This is going to be sig 33. This is going to be E22. This is going to be 11. 1, 1. And let's go ahead and let's see if we can get this value. So, does it make sense? So stress in the 1, 1 is going to be positive. Yep. Looking at the drawing, it makes sense. E1, 1, positive. E2, 2, positive. All right. Everything's looking okay in the world. So those are our values. We've got it. So the stress strain tensor just quantitatively. Will this material yield via under the stress state? So let's look at the yield stress. So the yield stress here, let's say my sigma y is, so sig y is equal to, and actually let's go ahead and write out. So my stress is going to be equal to basically, let's do, my sigma 1, let's just write it out. So I'm going to just kind of define these values. So my sigma 1 is equal to this. So my sigma 1, 0, 0, my 0, sig 2, 2, 0, and 0, 0, sig 3, 3. So this is my stress tensor right here. So I've got that. So my sig y, we just said, is around like what? Sorry, let's look at it one more time. Let's say it's around like 9 megapascals. So 9 times 10 to the 6. So is Rankine, so is sigma 1, sigma 1, 1. So actually, let's define this here. So this will be 10 times 10 to the 6. This is going to be 15. So my sig 1 equals 1.5 times 10 to the 7. My sig 2 equals this right here. And my sig 3 is equal to 0. So is my sig 1 greater than sig y? Yep. So this will yield. Is my sig 1 minus sig 3 greater than sig y? Yep. And then does it ask me for the von Mises? Was I that mean on this exam? Let's look at it. Oh, I was. Oh, Professor Steimel, you are just super mean. So let's go back. Let's look at our, again, that's why we want to have these notes ready to go just in case I decide to ask a question like this. Probably not this year, though. We'll see. I might have some more interesting questions up my sleeve. So let's go ahead and look over here. So I'm going to do that sig effective equals square root of 1/2 times my sig 1 minus sig 2 squared plus sig 2 minus sig 3 squared plus sig 3 minus sig 1 squared square root. So is my sig effective, sig f, is it greater than sigma y? All yielding. There you go. That's it. So let's go ahead, let's go back to our problem, let's see what else is asking us to do. So finish this one, we finish this one, and then finally write out the full principal stress tensor, draw the rotation required to get there. So if you look at our stress tensor, we are already in the principal stress, so we're good. For the maximum shear, 45 degrees, we know that. So if we're already in, so 45 degrees. Draw the 3D Moore circle for the principal stress state, so the maximum value of shear. So tau sigma, so this would be my sigma 1, this would be my sigma 2, this would be my sigma 3, so circle, circle, circle. What's the maximum value for shear? It's just going to be sigma 1 minus sigma 3 divided by 2, tau max. That's it. There we go. That's essentially the problem. So number 2 done. So not too bad. So I will see you all in the next video, and let's get into problem 3, which is I'm lost. Help me navigate my deformation mechanism maps. See you next video. Thanks.